Hello, welcome to this channel. We would be kicking off the complex analysis playlist. In this playlist, we would start from scratch, from the basics of complex numbers, and take it as far as the Lorentz series, as far as integration in the semicircular contour. All of these are very, very important bits in complex analysis. So within this playlist, we'll be taking it bit by bit, of course, but the entire playlist will cover every single thing you need to know as far as complex analysis is concerned. As always, don't forget to like, share, and subscribe. And of course, turn on your notifications so that you would know when the new videos come up. So let's begin. Now for today, of course, as I've said, in this module, we'll be looking at the concept of the complex number. Now for the complex number, we have to take it by set theory and look at the relationship it has with the other kinds of sets of numbers that we have. Of course, we know that the basics of elementary mathematics is the set of natural numbers, which is completely contained in the set of integers, which is also completely contained in the set of rational numbers, which is then completely contained in the set of real numbers, which we say is the universal set for basic mathematics. However, the set of real numbers in itself, where we expand into advanced mathematics, is also completely contained in the set of complex numbers, which is what we are studying. Of course, you can consider complex analysis as the study of complex numbers and its properties. Now, of course, just as you know that the real number is the union of rational and irrational numbers, we can also now discuss the complex number itself as a collection or a combination of real numbers. Now, how? Consider the basic complex number, which is of course an element of the entire set of complex numbers, can be written as z is equal to x plus iy. Now we say this x is the real part, and then we say this y is the imaginary part. Now, the combination of these parts gives us the complex number. However, you'll notice that x itself and y itself are both real numbers. So in order to formulate the complex number, you combine two real numbers together and put in the addition of I. Now, what is I itself? I is the basis for complex analysis, the basis of complex numbers, and I is in fact equals to the square root of -1. This is the basic foundation for what complex numbers stand for. Essentially, we can see that every real number is a complex number, but not all complex numbers are real numbers. For instance, if we say the number 3 is of course a real number, it can also be written as 3 plus 0i, which will then make it a complex number. However, if you have 2 plus 3i as a complex number, 2 plus 3i cannot be a real number because of the fact that this I in itself is not considered a real number. So this I itself is where that distinction arises. But for any real number, we can just simply add 0i to the back, because we know 0 times anything gives us 0. So it makes it easy for us to see that every real number is a complex number, but not all complex numbers are real numbers. Now that we have talked about this formulation of the complex number and where it stems from, let's now talk about the different forms in which we can rewrite the complex number. Now, we have looked at the first form, which is the algebraic form. We have written that before, z is equal to x plus iy. This is termed the algebraic form. However, we also have the polar form or representation of complex numbers, which is written as z is equal to r cos theta plus I sine theta. And then we also have the exponential form, which in general is written as z is equal to r e raised to the power I theta. Now, of course, we know what x and y is. X stands as the real part, which is also a real number, and y stands as the imaginary part, which is, of course, also a real number. Now, for r and theta, what exactly do they stand for? R is called the modulus of z, which is also called the radius of the domain formed by z. We'll get to see more of that later on. And then we have theta, which is also termed the argument of z, right? Which is the angle formed by that complex number within that domain. We will also get to see more of that, as well as the formulas necessary for finding what the modulus or argument of a complex number is. Now that we have looked at the basis of the complex number, of course, remember this is the preliminary introduction to what complex numbers stand for. Let us now look at the various operations we can have under complex numbers. Now, the first common operation we can have is the operation of addition. Now, for complex numbers, addition is done component-wise, which means real part will add to the real part, imaginary part will add to the imaginary part, right? Think about complex numbers the same way you think about vectors in real analysis. For vectors, you add component-wise. The same thing happens for complex numbers. You also add them component-wise or part-wise in this case. So for instance, let's say we have z1 to be equal to x1 plus iy1. And then we also have z2 to be equal to x2 plus iy2. Then if we had z1 to z2, then the operation would be the addition of the real parts plus I addition of the imaginary part. This would give us the result for the addition. The same thing also happens when we discuss subtraction. For subtraction, if we have z1 minus z2 remaining or retaining the same meaning or representation for z1 and z2 as above, you will have x1 minus x2 plus I y1 minus y2 as the result. Now, this is exactly how addition and subtraction works as far as complex numbers are concerned. Now, when we now talk about multiplication, this time around, multiplication is done using the expansion method as you normally do it for various functions in real analysis. Now, how does that mean? If we have, as always, z1 times z2 remaining or retaining the representation of z1 and z2, we would have x1 plus iy1 multiplying x2 plus iy2. Now, in this case, what would we have? We would have the same way we expand. X1 will multiply the entirety of z2, and then iy1 will multiply the entirety of z2. The same way we do multiplication outside, such that if we were to carry out this multiplication process and expand, we would have x1 x2 plus I x1 y2 plus I y1 x2 plus I times I gives us I squared y1 y2. This is the representation we would have for the multiplicative process. Now, every complex number in its algebraic form must be able to be represented as real part plus I imaginary part, which is exactly this form. So it means that even if this is this full representation, we must be able to constrain or combine it or find like terms such that we can rewrite it in this form. Now, how do we do that? Obviously, I is common in these two places, so we can factorize. That is fine. However, we have I squared here. How do we deal with powers of I? Do not forget that we have said that I is equal to the square root of minus 1, and that's the basic principle for complex numbers. So if I is equal to the square root of minus 1, it would imply that I squared will be the same thing as I times I, which would be the same thing as the square root of minus 1 multiplied by the square root of minus 1, which, of course, by this multiplication will give us minus 1. Because root minus 1 times root minus 1 would give us minus 1. That's the same principle of surd multiplication. Similarly, if we go I cubed, would have I squared multiplying I, which would be minus 1, which is I squared, multiplying the root of minus 1, which is our answer will be minus I. Similarly, if we have I raised to the power 4, it will be the same thing as I squared multiplying I squared, which would be minus 1 multiplying minus 1, which would give us 1. From there on, every other thing follows cyclically. I raised to the power 5 is the same thing as I raised to the power 6 is the same thing as I squared, which is the same thing as minus 1. I raised to the power 7 is the same thing as I cubed, which is minus I. And then I raised to the power 8 is the same thing as I raised to the power 4, which is equal to 1. So using that in this representation, it therefore follows that for Z1 multiplied by Z2, we would have x1, x2 plus I x1, y2 plus I y1, x2 minus y1, y2 because I squared is minus 1. So we can now bring together the real parts x1, x2 minus y1, y2, and then we can then bring together the imaginary part x1, y2 plus y1, x2. And this would give us the full representation of what the multiplication of complex numbers looks like. So we have looked at the meaning of the complex number. We have also looked at the operations that the complex number fulfills, right? And with this operation, of course, every other kind of operation will also fall in place. So there you have it. In our next video, we will discuss the Argand diagram, which is the graphical representation of the complex number. We will shed more light into the meaning of the modulus and the argument, as well as other kinds of operations that are necessary as far as complex numbers are concerned. As always, do not forget to like, share, and subscribe. Turn on your notifications so that you know when we drop new modules or videos within the playlist. Thank you.